Okay, hi everyone. In this video, I want to talk about philosophically why we even care about induction or well-ordering. We already know that these two things are kind of equivalent in the sense discussed in the previous video, so you should watch that one if you haven't yet. But just knowing that those two concepts are equivalent doesn't really tell us that they're useful, right? Why do we even care that induction is the thing we can do? Why do we even care that the natural numbers have this well-ordering property? So to answer that question, I want to go through the proof of a pretty basic statement, and the claim is this. So claim. Let x be any natural number then x squared plus x is even. Okay, that's our claim. It's easy to check that this is true in a few specific examples. You could try x equals 1. Well, that would be 1 squared plus 1. That's 2. That's even. Okay, let's try some other examples. X equals 5. That would be 5 squared plus 5. That's 25 plus 5. That's 30, which is also even. Okay, and you can try any example you like. I promise this is really true. So how do we prove it? It seems like there's kind of there's one kind of proof that might seem tempting, I guess I want to say. And so I'll put in quotes, proof, because it's not really a proof. You could imagine trying to prove this by saying 1 squared plus 1 is 1 plus 1 is 2 is even. Nice, okay. 2 squared plus 2 is 4 plus 2 is 6 is even. Nice. Okay, 3 squared plus 3 is 9 plus 3 is 12 is even. Also checks out. And you could and then you could just like continue on in this fashion. So you could say ... right? And then you draw a little QED box and you'd be very happy with yourself. The issue is that this isn't a proof at all. This isn't telling us that no matter which natural number I pick, I'll definitely get an even answer, because you've just done specific calculations in each particular little subcase. So who knows if there's any pattern to these calculations? Who knows that this will continue on forever? You really have to prove that somehow. Okay. So what's some other kind of attempt we could have? The idea instead is to use induction. So the real proof is by induction. So we're going to use the well-ordering theorem. No, sorry. So the real proof is by induction. And the way that's going to work is we need to choose a proposition that depends on a natural number. And we want to prove that proposition for all natural numbers. That'll be our goal. So this is some statement we want to prove for all natural numbers x, right? P of x squared, or x squared plus x is even. So in our proof, let's let that be our proposition. Let P of n be the proposition, n squared plus n is even. And let me just be extra precise about what I mean by even, just so we know we're actually proving things very rigorously. What I mean by even is that there exists some natural number k such that this number that I claim is even, n squared plus n, that's what I claim is even, this has to be 2 times k. So all I'm saying is a number is even if it's equal to 2 times some other number. So I want n squared plus n to be 2 times some natural number. Okay. So the idea is, if we can prove that P of n is true for all n, then we'll know that our claim is true in general. So this was the proof just right here. This would be a proof of P of 1. This would be a proof of P of 2. This would be a proof of P of 3. And I guess in this video I will be assuming that 0 is a natural number. So I probably, in this purported fake proof up here, I should have started with this case here. I'll be using that convention, that 0 is natural. Okay, so when we're going to do our inductive proof, remember that the principle of mathematical induction tells us we need to prove a base case. We need to prove that P of 0 is true, and then we need to prove that whenever P of n is true, then so will P of n plus 1 be true. Okay, so let's start with P of 0. P of 0 is the statement, there exists a k and n such that n squared plus n equals, n here is 0, such that 0 squared plus 0 is 2k. So P of 0 is true because we can choose k equals 0, because 0 squared plus 0 is 2 times 0. Okay, that was an easy base case. In general, the base cases of inductive proofs are going to be easy. In our inductive step, the way this works is we suppose P of n is true, and we try to deduce that P of n plus 1 is true for some arbitrary n. So we're going to let n be arbitrary, and suppose that P of n is true. So what does it mean that P of n is true? It means that there exists some k in n such that n squared plus n is 2k. And now what I want to do is show that there is some natural number, let's say L, such that n plus 1 squared plus n plus 1 is 2 times L. That would be the statement of P of n plus 1. I want to show that P of n plus 1 is true. Okay, so how am I going to do this? I'm just going to look at what happens when I take n plus 1 squared plus n plus 1. This is the thing that I want to show is even when I look at P of n plus 1. So let me just expand this out. That's n squared plus 2n plus 1 plus n plus 1. That's in n squared plus n. I'm going to leave those two terms right here. And then my remaining terms are this 2n, this 1, and this 1. So that's going to turn into a plus 2n plus 2. And now I'm going to notice I knew that n squared plus n was equal to 2k. So that's 2k plus 2n plus 2. But now I see I can just factor stuff out. So it's a 2 times k plus n plus 1. And the next thing I have to say is, since k and n are natural numbers, k plus n plus 1 also is a natural number. Therefore, what I just did is I showed that n plus 1 squared plus n plus 1 is 2 times some other natural number, and that's precisely what it means for P of n plus 1 to hold. Okay, so then I complete the proof by just saying, by the principle of mathematical induction, P of n is true for all natural numbers n. And hence, we have the desired claim. So you just write that. Great. So that's a real genuine proof of this statement. And let me just comment on why induction is so important for this. We used induction here to kind of prove infinitely many things in finitely many steps. And the finitely many steps part is important. If we were allowed to have proofs that were infinitely many steps long, then presumably we could have made some proof like this. But it's kind of clear that this shouldn't be a valid proof. This shouldn't be a valid proof strategy, because no matter how long someone goes and writes out all these different special cases and checks that they're all even, surely they can't have written down all the cases. Or even imagine some hypothetical situation where someone did write down all of these infinitely many different proofs of each little individual subcase. How can you be sure that they're correct? You can go and check each line one by one, but you'll never finish checking the lines, so you'll never actually be able to finish checking that their proof is correct. So it's important when you're writing a proof, right? The point of a proof is not just to convince yourself that the fact is true, but when you're proving something, the point is also to write down some sequence of logical statements that could convince any rational reader that the proposition you claim is true is actually true. And so if you write down an infinite collection of individual little subcase proofs, it's just impossible for anyone to go and check all those cases. So it's not a valid proof because no one can actually go and verify that the proof you wrote down is legit. So that's an important property of proofs. And as a result, we need our proofs to be finite in length. Every proof can only consist of finitely many statements. Each one has to follow logically from the previous statements that you've made. So that's the usefulness of induction. Let me put that as a slogan. Induction is useful because it lets us prove infinitely many things. In finitely many steps. Which really seems like a wild, crazy thing that's even possible. The trick here is really just that our infinitely many things are given by a universally quantified statement. So the thing we're proving in the end is that for all n and n, p of n is true. And so that's kind of one statement that we've split into infinitely many statements, and then we use the trick of induction to prove all of those infinitely many statements that we split up into in just like one little magic trick using the inductive proof. Okay. So that's why induction is useful, is because it actually allows us to implement this strategy of taking a statement that's something has to happen for every natural number, and we break that statement into a different proposition for each natural number, and then we prove all of those infinitely many little sub-propositions using induction in finitely many steps. So it's a helpful technique in that way. And as we saw, induction is really exactly equivalent to the well-ordering theorem. So it should be the case that any inductive proof could just as well have been done using the well-ordering theorem. And that's true in this case as well. Let me just quickly outline how that would have gone. Usually, when you want to convert an inductive proof into a proof that uses the well-ordering theorem, so from the principle of mathematical induction being the strategy to an application of the well-ordering theorem being the strategy, what you do is you work by contradiction. You suppose that the claim you want to prove, that for all natural numbers n, p of n is true, you suppose that claim is false. So in other words, that there exists some natural number n such that p of n is false. That's your initial assumption for contradiction. And so if you assume that that's the case, then the set of natural numbers n such that p of n is false is not empty. You can apply the well-ordering theorem to that set and extract a minimal counterexample, a minimal natural number n such that p of n is false. And from there, you can hopefully produce some contradiction. For example, in this case, if n plus 1 was the smallest natural number, so that n squared plus n was not even, we would immediately have a contradiction, because we would have supposed that this is not even, and we would have supposed, and therefore this is not even, but this is clearly even, and that means that n squared plus n is even, and that contradicts the fact that n wasn't the minimal element of our set. So if that was confusing, I'm going to go through that in much more detail in an example of a second proof here. So this time, I'm going to have a different claim. And the second claim is going to be that every natural number which is greater than or equal to 2 has a prime factor. Okay? So for example, 15 is a number that's bigger than or equal to 2, and 15 has a prime factor. 3 is a prime factor of 15, and 5 is a prime factor of 15. Any prime number is a prime factor of itself, that sort of thing. Okay, so normal kind of prime factorization things. And so this is the claim. Every natural number greater than or equal to 2 has a prime factor. This should seem kind of intuitive. We in fact know that every natural number greater than or equal to 2 has a unique prime factorization. So not just that it can be divisible by at least one prime number, but you can totally break it up as a product of primes. But besides that, that maybe needs a little more effort to prove than this. So for this claim, we're just going to take this very simple statement that every natural number greater than or equal to 2 has at least one prime factor, and that's all we want to show. And our strategy here is going to be to use the well-ordering theorem, which we know is equivalent to induction. And like I said, when you're using the well-ordering theorem to prove some kind of thing that you would otherwise do by induction or something like that, a good strategy is to work by contradiction. Or generally, this is the way to invoke the well-ordering theorem. So suppose for a contradiction that there exists some natural number n such that n is greater than or equal to 2, and n has no prime factor. Okay, so this is just supposing the negation of what we want to prove. I want to prove that every prime number, every natural number greater than or equal to 2 has a prime factor, and I'm going to suppose that that's not the case, and we'll deduce this contradiction. So how am I going to do this? I'm going to define a set. Let me define the set S to be the set of natural numbers n, such that n is greater than or equal to 2, and I guess I should use a different letter here. Let me, for this natural number that we had here, some exists some n naught, let me say. This will be n, that'll be n0, and then now I'll have n free to use. Okay. So, so I'm going to let S be the set of natural numbers n such that n is greater than or equal to 2, and n has no prime factors. Okay, so what does this mean? By the well-ordering theorem, S has a minimum element. That's because S is a subset of the natural numbers. Every element of S has to be a natural number in particular. But secondly, S is non-empty, because there is at least one natural number which satisfies this condition to be inside S. So S is a non-empty subset of the naturals, and as a result, the well-ordering theorem tells us that S has at least a minimum element. So let's call that minimum element X, let's say. So that means X is an element of S, and also X is smaller than every other element of S. So let's see what that means. Okay. We're going to consider two cases. Case 1 is where X is prime. Well, actually, let me not even split into cases. Let me just kind of handle it one step at a time. Let me say that X cannot be prime because X has no prime factors. That's because X is an element of S. So X is an element of S, which means that X has no prime factors. And if X was prime, then it would have a prime factor. It would be a prime factor of itself. So in fact, X cannot be prime. Okay? Thus, X is composite. So I guess at this point, I need to specify, I really should have done this already, but let me just specify exactly what I mean by prime. Kind of silly for me to even start proving this claim before we knew exactly what prime meant, but just for, well, I guess I messed up there by not doing that, so let's correct ourselves now. Let's write down the definition of prime. Natural number n is called prime if natural number n is called prime if, first of all, n has to be at least 2, and secondly, if m is a natural number such that m divides n, so in other words, that means n over m is an integer. So I'm just saying that, like, for example, 2 divides 4, 2 divides 8, but 2 does not divide 7. 2 doesn't go evenly into 7. So if there's some divisor of m, I just have m is some factor of n, then m equals 1 or m equals n. So a prime number for us is just a natural number which is greater than or equal to 2, such that the only two divisors of this number are 1 and itself. So that should be a pretty familiar definition of prime, hopefully. And let's return back to our proof now. So now that we know that x is not prime, what does that mean for our number x? Not being prime means that one of these two conditions must hold. So either n didn't satisfy this property that n is greater than or equal to 2, or n didn't satisfy the property that any divisor has to be 1 or itself. So let me write that formally down below. Thus, x is less than 2, or there exists some m such that m divides x, and m is not equal to 0, and it's not equal to x. Well, x is greater than or equal to 2 because it's an element of S, right? X was an element of S, and every element of S has to be at least 2. So x can't be less than 2, so it must be the latter. So there is some m in n such that m divides x, and, sorry, that should be a 1 here. M not equal to 1 comma x. And m is not 1, and m is not x. Okay, so what does it mean that m divides x? It means that x over m is an integer. So let me make note of that. This means that m over x this is actually going to be a natural number. This is going to be a positive integer. That's because m has to be positive. So m divides x means that m has to be at least 1, and m is not either 1 or x. So certainly, sorry, this should be an x over m. So x is neither 1 nor x, or m is neither 1 nor x, and so that means that x over m has to be bigger than 0, because m is positive and x is positive. So this is a positive integer. So let me actually just say in particular it's a natural number. Also, notice that m is not equal to 1, so m is at least 2, right? So that means x over m is less than or equal to x over 2, because m is at least 2. And of course, that's less than x. That's because this part here is because x is greater than or equal to 2. So if x is at least 2, then x over 2 is going to be strictly smaller than x. And so this tells me that x over m is strictly smaller than x. Okay? And what's more, not only is x over m less than x, we're also going to have that x over m is greater than or equal to x over x minus 1. And so this is coming from the fact that m is less than or equal to x minus 1. That's because m is a divisor of x, it's a factor of x, so it has to be less than or equal to x. But it's also not equal to x. So m is actually strictly less than x. And maybe a better way to write this. Since m is strictly less than x over m has to be strictly greater than x over x. And x over x is just 1. Okay, so that's maybe a better way to say that. So what we have here is a number x over m, which is bigger than 1, and it's less than x, and it's an integer, and that means x over m is an element of the set of natural numbers such that n is greater than or equal to 2, and because x over m is less than x, we know that x over m is not an element of S. That's because x was the smallest element of S, and x is bigger than x over m, so x over m can't be an element of S, or else x wouldn't have been the smallest. Therefore, x over m is not an element of S. What did it mean to be an element of S? Being an element of S meant that you have no prime factors. So not being an element of S means that you do have prime factors. This tells us that x over m has a prime factor. Okay, so what does that mean? That means that there exists some natural number k such that x over m is p times k. P is some factor of x over m. Okay. But now we have a prime factor of x, right? X is just x over m times m, and that's just pkm. So p is a prime factor of x. Okay, but of course, this contradicts the fact that x is in S. X was the smallest element of S. In particular, it's an element of S. And every element of S is supposed to have no prime factors. But here we just prove that X does have a prime factor because a quotient of S did. So that's a contradiction. And we had assumed at the beginning that the claim was false. We supposed for contradiction that there was a natural number such that n greater than or equal to 2 and x has no prime factors. And we found a contradiction, so we have the desired claim. So I'll just end the proof there. But hopefully that's an interesting way to apply the well-ordering theorem to try to solve problems. We could have done this by induction too. It just so happened that in this instance, it was easier to use the well-ordering theorem, and the reason is that when we called upon a previous smaller number, we didn't know where that smaller number was. So in an inductive step, you're trying to prove that p of n implies p of n plus 1. So you're using the previous number, the previous case, to prove the next case. But in this situation, what we used was we had kind of our smallest counterexample x, and then what we did was we looked at x over m. And we don't know what x over m is. Maybe x over m was just like x minus 1, that's possible. But more likely x over m is like x over 7 or something. It's very far from x. And so it's not necessarily the case in this theorem, in this proof that used the well-ordering theorem. It's not very easy to see how to write this as a standard inductive argument where you only use the value where you only use like p of n to prove p of n plus 1 instead of just like all the previous p's. And so there is an adjusted version of induction called strong induction that does this for you without a contradiction. And we could have used that as well here. But so hopefully, at least this was kind of an interesting example of why the well-ordering theorem might be an interesting thing to try to use in your inductive proofs. It might be a little easier for some proofs than straight induction might be. And so if you're still not convinced, please do go and try to prove this second claim, claim number 2, using induction. If you feel like, what's going on, these properties are supposed to be equivalent, it should be easy to write an inductive proof of this. It is really not too hard. It's totally possible, and I encourage you to try to do it. But I think this is by far an easier approach. Okay, so that's all I wanted to say there. And I think this will probably be the last video in the series.